So it's this one. All right. Hello, everyone. Hello? Okay, is this better? No? You can lower it a little bit. Okay? This is better? Okay, can everyone hear me right now? It's clear? Perfect? All right, awesome. Hope you had a nice lunch. So, welcome to the first AI session for Invisible Garden. My name is Pedro. I'm an AI researcher. I work for a company called Colossian, and in there I research video generation pipelines specifically for animating avatars. But here we might touch on that maybe on the last lecture. But for the AI sessions, I'm going to be walking you through a lot of different AI algorithms in machine learning also, and we'll take a look at like the landscape in AI basically, and then build up until we get to the fancy algorithms that you know from like the latest research. So let's start with what is AI exactly. So AI is the broad field of making machines that perform tasks that typically require human intelligence. So this is kind of a broad definition on purpose, and because you can call a lot of different stuff AI, any kind of intelligent system that you program, you could theoretically call it AI. Once we start getting into machine learning, that's where the definitions get a little bit more specific. So machine learning is a subfield of AI that focuses on systems where we don't program the system to perform a certain task explicitly, and instead of that, we provide it data, and the system learns the task from that data. So inside machine learning, you have a lot of different algorithms that we'll touch on, from like simple linear regression to data visualization and dimensionality reduction algorithms like principal component analysis, like decision trees. A lot of algorithms that were developed a long time ago. And included in machine learning, we also have neural networks, which is the technology behind most of the recent advancements in AI that you hear about, for example, large language models and video generation models and all of that. So neural networks are basically a class of machine learning models that are composed of multiple layers of artificial neurons. And by having this composition of a lot of layers of neurons, we can model a lot more complex tasks, like, for example, generating or understanding text, or generating videos, or understanding images, for example. So this is what we'll learn about when we touch on deep learning, which is essentially how to use like these very deep neural networks to learn to do these more complex tasks. And inside of deep learning, it's where you also find, for example, the field of, or the subfield of Gen AI, which is a subset of deep learning algorithms that focus on generating new content, like text or images. And this is basically where you have the state-of-the-art algorithms that you hear about nowadays. Throughout these AI sessions, I'm also going to touch upon privacy in the AI and machine learning field. This is not my expertise, but I'll do my best to research a little bit of the intersection between AI, machine learning, and, for example, zero-knowledge proofs or encryption, or talk a little bit about differential privacy, which is something someone mentioned today. So we'll touch on that probably this Friday during that lecture. So let's get going. So, by the way, the font might be a little bit too small, but I sent you the slide presentations on Discord, I believe on the announcements channel. So, awesome, you got it? So if you want to follow it there, maybe it's better so you can read a little bit of the smaller fonts. But yeah, in any case, I'll go through what it says there. So let's go a little bit about AI history. So AI basically is a field that developed basically alongside the development of computers. And even before we had computers, we were already doing thought experiments with AI, like for example, the Turing test. So as soon as we started getting the first actual computers around the 1950s, that's where we also get the first instances of AI algorithms, like the first perceptron, which is like this kind of model of an artificial neuron that we'll explore later during the sessions. You also get like the first AI programs, which basically were just very complex if-else and loop logic at the time, but you could already call these like, artificial intelligence. You get the first chatbots, which is, this one was called ELISA, and they achieved this not with the large language models that we have today, but using just complex understanding of the language and modeling every single aspect of a language in order to be able to respond appropriately. And then from the 1950s until the 1970s, there was a lot of hype around AI. A lot of promises that it would automate everything, and so there was a lot of research put into it. But then, after some point in the 1970s, this research kind of died out because people kind of realized researchers were doing a lot of promises and not really keeping up with them. So for about a decade in the 1970s, we stopped, or we didn't stop, but research in the AI field kind of died down. And it only picked up again in the 1980s when we started getting the first instances of artificial neural networks, which were kind of a breakthrough and showed us that we could teach machines to learn stuff by themselves and actually model, for example, the way the human brain works. And so this kind of kicked research back up again. But still, like the computational power at this time was very limited, so we couldn't really teach machines to do anything useful besides just proofs of concepts for these artificial neural networks. And so we had a little bit of a second winter in AI until the computational power kind of picked back up or like developed a little bit more. And then we actually started getting useful applications of machine learning and AI. And that's, for example, when we got Deep Blue, the first machine to beat a chess player, Garry Kasparov. And we got a few instances of the first robots. And then a little bit later, like throughout all these years, AI kind of started developing. There were a lot more AI researchers. And we started getting a revolution in terms of deep learning. So what kind of marked this revolution was something called AlexNet, which was the first neural network that was able to classify images with a good degree of accuracy. And this kind of showed everyone, okay, deep neural networks can actually be very useful. And so research kind of picked back up, and we got all the most recent innovations like transformers and generative neural networks and ChatGPT and Sora, for example, and all of that. So yeah, we'll touch a little bit on the algorithms that kind of started all the way from the 80s, for example, and kind of build our intuitions of these concepts of what are neural networks, for example, or what are like regression algorithms or classification algorithms. So we can then finally get to the juicy stuff and understand all of that. So let's get into machine learning. So machine learning can kind of be split in a lot of different ways, but one of the most common ones is splitting into supervised learning, unsupervised learning, and reinforcement learning. And for example, within supervised learning, you have different types of algorithms, and the main distinction there is like between classification and regression. And we'll see what this is a little bit later. And so for each of these subcategories, you have a lot of like different algorithms. We won't go through all of them, but I'll show you and explain to you like the most important ones throughout the next lectures also. So today I'm just going to do like a very brief introduction of like the basic categories of machine learning and what we can achieve with them. So let's start first with supervised learning. So supervised learning is essentially trying to have a machine learn a task, giving it a data set of examples, like inputs X and the expected outputs or the expected labels of the inputs, and we call this Y. So supervised learning is basically learning a function, which is like Y as a function of X, the input, as best as possible. And this can be split into two different kinds of tasks. So one of them would be classification. And in classification, our Y is basically a label or a class. So for a given set of inputs, for example, here in the image, let's say your Y and your X, or let's say the vertical and the horizontal axis are two inputs. So this is a 2D X, like a vector. And for each element in the plane, you can either have a class which is like an X or an O. And the goal of a classification algorithm is to learn to map the X's to the labels. This is different from regression. Regression is basically learning a function which has a numerical output. So in this case, for example, we have in the horizontal axis we have an X, like the input, but in the vertical axis we have the output. And we have several points in this space, and we need, like regression is basically trying to learn a function that can approximate and predict the Y values from the X values. So this is slightly different from above, because in classification we're trying to learn a class for each sample, and in regression we're trying to predict a numerical value for each sample. So with this kind of algorithms, we can already achieve a lot of stuff. For example, if we have an email classifier, we can use it to predict whether an email is normal or it should go in the spam folder, for example. For example, for regression algorithms, we can, for example, use them to predict the price of a house based on the number of square feet in the area. Or we can predict the house prices, for example, based on the region of the map. And so, for example, for each coordinates, or each pair of coordinates, like longitude and latitude, we can predict a value, which is the value of the house. And we can use also other inputs. So regression algorithms kind of, like you learn to predict the value, the output, like the price of the house, based on multiple inputs. And this can be 2, can be like 100 if you want. Depends on your data set. And then we also have other kinds of classification algorithms. For example, for fraud detection, our inputs may even be like graphs. We don't need to stick to like numerical values or vectors. We can, for example, use graphs as an input and train a classifier to predict whether certain nodes in that graph are, for example, normal bank accounts or they're fraudulent bank accounts, for example. If we have a graph of connections, which could be, for example, transactions between bank accounts. And for example, we can also apply this to images, because images are essentially blocks of numbers. So your input is going to be very high dimensional, but the principle is the same. So you learn to predict, for example, the class of an image, whether an image has a cat in it or a dog, for example. And then there's other types of tasks, for example, like object detection, in which case you're trying to predict the numerical values of a box around the object. So in this case, this can be seen as a regression problem, or kind of a mix of regression and classification, because in the end, you're also trying to predict the class of the object that's inside the box. So these, like regression, classification, aren't like really fixed categories. It's just one way to describe this kind of algorithms. But for example, for object detection, you can have both. And for image segmentation, you're actually classifying each pixel individually. So it can be seen as a classification problem, but with multiple outputs, not just one output. So the goal here is basically just to show you that there's a lot of different types of algorithms, and we'll try our best to go through a lot of, or some of them. Okay, so now let's go into unsupervised learning. So with supervised learning, we have a data set with our inputs and outputs, and we're trying to predict a function from the inputs to the outputs. With unsupervised learning, we basically only have a data set, and we don't need to have any labels on that data set, and our goal is to extract information from the data set, even without any kind of labels. So some types of algorithms include, for example, dimensionality reduction. And in this case, we might, for example, have a very high dimensional data set, and we want to visualize it. And so we want to bring it down, for example, to 2 dimensions. And there are algorithms that allow us to do this in a way that preserve as much information and as much structure as possible from the data set. You can kind of think about it as if you have a cloud of points in high dimensions, you pass, for example, if you want to bring it down to 2 dimensions, you pass a plane through that cloud of points in a way that captures it in the best way possible. And so in the end, you can visualize data that lives in a much higher number of dimensions. And another type of algorithm is clustering. And so in this case, you also have just a data set of points, and the goal is to find clusters of points within that data. And this can be done in several ways. We'll look into this probably on Wednesday, I believe. So one good example, for example, of unsupervised learning, I found this recently on LinkedIn, and here they took a survey from several countries. People answered the survey from several countries, and they also had ChatGPT answer the survey. And they tried to look how the answers from ChatGPT relate to the answers from all the other countries. And in this case, this survey has a lot of questions. It's probably from a scale of 1 to 5, how much do you relate to this sentence, let's say? And you have people fill out, for example, 100 of these questions. So your data is going to have 100 dimensions. So in order to kind of look at what's going on and get a big picture, you have to bring it down to 2 dimensions. And so they use this kind of dimensionality reduction technique to plot all the answers in a 2-dimensional space, so you can kind of visualize how close the answers for each of the countries are. And then they run a clustering algorithm on top of this. So they kind of group the countries into different classes. It doesn't necessarily correlate with geographical location. But if you try to interpret it, you can kind of figure out certain dimensions that make sense. For example, in this case, yeah, if you you have kind of you can get a sense that more or less this way you get a more Western culture, and this way you get a more Eastern culture, for example. And you might argue that maybe this direction you have a little bit hotter climate, and this direction maybe colder climate. I don't know. This kind of algorithm doesn't tell you what your axes are going to be, but that's up to you to interpret. But at least it gives you some way to look at the data. Okay, let's get going. Okay, so the final category of machine learning algorithms is reinforcement learning, and this is different from the other two, since the goal of reinforcement learning is to teach an agent to interact with an environment in a way that maximizes a certain reward. So an agent can act in the environment and it will act as a function of the observation of the state of the environment. And then based on the agent's action, the environment is updated and reaches a new state, and it can also provide a certain... Whose cell phone is this? I think someone's out to get it. Yeah. It's up there, I believe. Okay. Okay, we're good. So as I was saying, so the agent performs an action in the environment, and the environment updates to a new state, and the agent may also get a reward based on this. And so the goal of reinforcement learning is to train an agent to act in the environment such that it maximizes all the rewards that we will get in like a possibly infinite time frame. So it's not just learning to map an input to an output, it's like teaching an agent to act. So it's a fundamentally different kind of algorithm, but it's still machine learning. And we'll also look at this possibly in the second week. So there's also a few different examples for reinforcement learning. For example, AlphaGo was the first algorithm that beat Lis et al. In the game of Go. And this algorithm is fully built on top of like a reinforcement learning framework. It's also been used to beat human teams in, I believe it's Dota 2, the video game. And it can also be used for self-driving and also for robotics to teach, for example, robotic arms to manipulate objects in its environment. And so the way these robotic arms are trained is that you build a simulator for them and you let them interact within the simulator and give them rewards, for example, when they pick up an object and put it in a different place. And so the robot within the simulation learns to do this task, and then you can apply it in the real world. So we saw one way to split machine learning or to give some certain categories to the algorithms within machine learning, but it's not the only way. I've also seen this concept of machine learning tribes, which I thought was interesting, and kind of gives you a broader perspective of all the possible machine learning types that you can have. Within these tribes, there's like 5 different ones. So one of them is the symbolists, and they work mostly with like rigorous logic and deduction techniques or inverse deduction techniques. There's the analogizers, which work or they build algorithms that work on the concept of if you want to classify, for example, a new sample, you look at all the other ones and you see which ones are similar and you do it based on that. So there's this concept of analogies, so you try to find the best examples on your data so you can predict a new sample. There's also the Bayesians, and they work mostly on using statistical algorithms and probabilistic inference. There's also the evolutionaries, so this is related to the concept of genetic algorithms, which you might have heard about before. And these algorithms, I'll go through them in a little bit. And finally, the connectionist is where we have neural networks. And basically, neural networks learn their tasks using gradient descent, which we'll also look at during a next lecture. So as I said, symbolists use formal logic. It's based on rule-based systems. And they use these like deduction and inverse deduction techniques. I have here like an example of inverse deduction. So inverse deduction is basically, so let's start with deduction. So in deduction, we start with logical rules and we apply them in order to derive new rules. This is kind of similar to the way mathematics is constructed. So you have axioms and then can then build theorems on top of these axioms and on top of previous theorems. Inverse deduction is different in the sense that you start with the data and then you try to infer logical rules that explain the observed data. And so we have here an example. Let's say we have some data regarding these kinds of relationships. So for example, the parent of Alice is Bob, the parent of Bob is Carol, and the parent of Carol is David. Actually, it's the other way around. So Alice is Bob's parent, Bob is Carol's parent, and Carol is David's parent. And we also know that Alice is an ancestor from David, and Bob is an ancestor from Carol. And so our goal here would be to do some kind of backwards reasoning and establish how this ancestor relationship connects to the parent relationship. And I'm not going to go into detail about how this works also because it's not my kind of area of expertise. I'm just letting you know that this exists. So you get like a complete picture of machine learning. So you can kind of reason through this data and figure out that you can have an ancestor of X is Y if X is Y's parent, or if X is Z's parent and Z is Y's ancestor. So this is kind of a silly example, but this kind of logic can be, or we can build much more complex examples of this. I'm not going to touch on this during the next lectures. I'm just showing you this because so you get like a complete picture of everything that's been done within AI. This is probably the initial way in which reasoning was done, and the kind of first intelligence systems that were built way back in the like 60s. But yeah, nowadays we tend not to use this kind of algorithms. So the other ones I talked about were the analogizers. And so as I said, whenever we want to classify a new instance, we look at the instances around it, or the closest instances to it. And we, for example, can infer that a new instance should be a triangle based on the fact that it's closer to more triangles than squares in this case. Or we can, this is called the K nearest neighbors algorithm. We'll look into that in more detail tomorrow. And there's another type of algorithm called support vector machines, which kind of tries to separate two different classes of samples in a way that's supported on the closest samples to the line, and these are called the support vectors. So yeah, this is one example of, or two examples of analogizer algorithms. In the Bayesian, so as I said before, here the goal is to reason under uncertainty, so it's very much based on probability theory and statistics. And they rely a lot in Bayes' theorem. So this is one of the fundamental theorems in statistics. And it allows you to estimate the likelihood of hypotheses and also to update your belief in certain hypotheses given observed data. Or as you get new data, you can keep updating your beliefs in the hypothesis. So for example, we have here another small example. Let's say we have an email and we have two hypotheses, which are either the email is spam or the email is not spam. And let's say we observe some evidence, for example, that the email contains the word wing. And we also have some prior beliefs. We can, for example, know that 30% of emails are spam and 70% are not spam. And we also know that if if an email is spam, there's a 60% that it contains the word win. And if an email is not spam, there's only a 5% chance that it contains the word win. So based on these prior beliefs and on the new information that the email contains the word win, we can use Bayes' theorem to predict the probability that it's a spam email given that it contains the word win. So you can do this with like very simple arithmetics. Yeah, I won't go through the math, so you can look at it if you're interested. So then the next class of algorithms is, or the tribe of machine learning, it's called evolutionaries. And this is where we find genetic algorithms or genetic search algorithms. So these are inspired by natural evolution, and they're very useful when you don't know the structure of a certain solution that you're looking for, or you don't know the structure of your hypothesis. So let's say we're trying to teach or like find a machine that can walk or jump. We have no idea like what this machine is going to look like. It could have like 2, 3 legs. It could have could just be a single line if we're like building it out of boxes. So there's like the space of solutions isn't continuous. And so in this case, the best approach is this kind of evolutionary algorithms. So the only thing you need is a way to turn a certain genetic code into your final solution, which in this case would be this set of boxes. And this genetic code would be, for example, the dimensions of each box and how they're connected to each other. And once you have this way of defining your solution based on this genetic code, you can initialize the random population of these solutions. You evaluate the fitness of each one of them. So in this case, you run a simulation and you see how far they jump. In this case, like the activations or the way it moves would also be included in the genetic code. And so you see which ones jump the highest or walk the furthest. And you use these best, the most fit elements of the population to create a new generation. So you can do this by applying crossover. So you combine genetic segments from the best elements, and you can also apply random mutations so that they can evolve. The best solutions can like find nearby solutions that are slightly better. And so you create a new population with this, and then you just keep generating new generations. And if you do this long enough, they'll start evolving, and the best ones will be preserved. And in the end, you'll have, or if you did everything right and your solutions can actually perform these tasks, you'll get a solution that should work well. Okay, and finally, we have the connectionists. This is where we will spend the most time during these AI sessions because it's where we find neural networks. So neural networks are essentially these simple interconnected layers of neurons. And so like a neuron can be seen just as a very simple summation operation. So if we have an input vector x, so we have, for example, in this case, 4 elements for x. We multiply each of them by a different weight, which are the w's, and we sum everything together. So the w's here would be essentially the connections in a neuron. X would be the input, and the neuron would be this summation operation. And then you pass the result through a nonlinear activation function. We'll see what this looks like in a following lecture. But this essentially will give you the output of this neuron. And then you can string together a lot of these different neurons in layers. So in this case, you have 2 input neurons, which are just your input vector. And then you have 3 hidden or like intermediate neurons. that get the inputs from the two input neurons, and they transform it using this summation, or they multiply it by the respective weights, they sum everything, pass it through a nonlinear function. Then you get a certain activation, so a new vector of values, in this case with 3 values in the middle. And then you repeat the process and you have like 4 new values. And in the end, you can like aggregate everything with a final output neuron and get a prediction. And then the way you train these algorithms is that you compare your predictions to the true values that you have, for example, in a data set. And this will give you an error. And this is what we call a loss function. The loss function is the way we take the predictions and the true values and we compare them to produce a certain error. And we train this neural network. So what I described until now is a forward propagation. And to train the neural network, we perform the backwards propagation, which is, it consists of calculating the gradient of the loss function in respect to all of the weights in the neural network. So maybe it's better if I explain it with the whiteboard. So when we pass it, oops, okay. So when we pass these, there's a speaker. Can we lower it? Okay. Hello? Okay. But maybe I'll do it without the mic. Okay. So when we pass a few samples through the neural network, we'll essentially create a space where we have, let's say our neural network has like 2 different weights, W1 and W2. And our loss function is going to depend on these 2 weights and create a sort of, so if we do this for multiple weights, in practice we don't do this, but we can visualize something like having a certain value here. Let's say like this. So this would be like a function. I don't know if this is clear, but let's say this is like the minimum value of these. This is like a convex well, let's say. And if we start with some random weights, let's say we start them here. This gradient computation, what it does, it's going to compute like the gradient of, this is the loss function. The gradient of the loss function with respect to the weights is going to be the direction in which this function increases the most in this space of the weights. So gradient descent is the process of going in the backwards direction. And so if you do this multiple times, you end up converging to like the smallest or the lowest value of the loss function. I'll have a picture here in a little bit, which might be clearer. Wait, where's the mic? Can you hear me still? Okay. Okay, I'll continue this way then. So yeah, the way these neural networks learn is by doing this gradient descent process, and this is done using backwards propagation. So this is backwards propagation. It's the process of computing this gradient for each of the weights in the neural network. So this is done in a backwards manner because we first need to compute the gradient of the final neuron with respect, or of the error with respect to the final neuron. And then once we have that, we compute the gradient of the error with respect to the previous neurons, and we kind of go backwards in the neural network. And at the end, we have the gradient of all the weights or for all the weights. This tells you the direction in which they increase the loss function the most. So we want to go in the opposite direction. And I think it's working like this. Is it okay? Better with a mic?
Yeah.
Okay, then let's do that. Let's get a mic, yeah. I might have... yeah, so this is kind of the picture I tried to draw. Maybe it's clearer now. But if we start with some random weights, we can keep doing this process of going down in the direction that's opposite to the gradient. And eventually we'll find the weights that give us the lowest possible loss function. And this means that our error is going to be very small. And so this means that our predictions are going to be very close to the true values. And this is basically how a neural network learns. We'll have a full lecture dedicated to this. This is only an overview, so at that time you'll have the chance to, or we'll have the chance to go a little bit deeper into this. I don't know, yeah, there's a mic. Thank you. Okay, there's also other types of machine learning applications that may not even fall within any of the categories that we saw until now. One of them is recommendation systems. For example, the type of algorithms that you see on Netflix to recommend you movies or on Instagram to recommend you posts. There's like two different types of recommendation systems. One of them is called collaborative filtering, and this is based on calculating similarities between users. And so if a certain user read something that you didn't, it's likely, if you're similar to that user, it's likely that you want to read that thing also, or watch that movie, for example. And the other one is called content-based filtering, which is trying to find the similarities between the actual pieces of content. And so if you saw something that's similar to some other thing, that other thing might also get recommended to you. One other application is, for example, time series forecasting. This can be used for like stock trading or predicting when a certain machine will fail, for example. You also have, for example, audio to text, and this can use a lot of different models, from like extracting features which are basically converting the audio to a format that's readable or understandable by a neural network, for example. And you can then have a neural network, and you can combine it with a language model, and that helps you produce the final text output. And one other application is natural language processing, which is understanding like language and predicting, for example, if the sentiment of a certain phrase is positive or negative, or in this case, Grammarly has this feature where you can predict whether each word is going to catch the attention of a reader more or less. So these kind of algorithms, some of them you can fit into the categories that we talked about. Some of them are kind of outside. So all of these categories are they're not like exhaustive. They're not meant to cover everything that's possible. They're just meant to illustrate or to try to categorize these algorithms and batch them together. So recently, one of the hardest topics has been Gen AI. So most of Gen AI is used or is done using neural networks. There's some other techniques that don't use neural networks, but probably in these sessions we won't talk about them. So most of the stuff you see here uses neural networks. So the best example is large language models, which are essentially next word prediction machines. But you can also, Gen AI also includes, for example, generating images or generating videos. In terms of generating images, one of the most common techniques until recently was GANs, so generative adversarial networks. And this worked by having a network generate a picture and then having a discriminator telling you whether that picture comes from a real data set or it was generated. And so based on this, you can compare it to the real label, so whether it was actually real or actually fake, and you get an error that you can use to backpropagate through the discriminator and through the generator and train both of them simultaneously. More recently, we have a breakthrough and we have a new technique called diffusion models. And these generate images or videos with a slightly different process. So we start with an image and we gradually add noise to it. And then we train a neural network to undo this noise. And so if we do this well enough, you can start with just a picture of full noise without anything in it. And you can give it to this network and it will gradually remove noise until you get an actual picture that's completely new. And so most of the recent algorithms that you see nowadays for generating images or generating videos are based on this technique. And myself, I work with this technique also all the time to generate videos of avatars and all of that. So you can also have, for example, text to speech models. And this can also use these generative adversarial networks. Or more recently, they can also use this diffusion process. You can also use neural networks to generate 3D shapes. For example, to generate assets for video games. And you can also use it to generate even movements. So when you play like FIFA, for example, or any kind of game, you control a player with your controller, and you're giving it very like sparse inputs. It's only like move left or up. But then the player ends up doing something far more complex. So you have to like kind of generate all of these movements and stitch them together. And for example, add a jump in the middle without you explicitly controlling all of the player's movements. So you can use generative AI techniques to create these movements in a way that's smooth. And finally, I would also want to touch upon the topic of privacy in AI and machine learning. I know of at least 3 different things that are at the intersection of these 2 fields. So one of them would be using fully homomorphic encryption within machine learning. And so this would allow you, for example, a client to encrypt their data, send it to a server to be run on a model while it's fully encrypted, and then get an encrypted result back, and only the client would be able to decrypt the result, but then the result would be the actual output from the model. And so in this sense, the model owner would never be able to look at your data, and this allows you to trust it or send data to it and have the responses without having to give out any information about your data. One other topic would be zero-knowledge machine learning. And what this allows you to do is to for a given input and model, you can produce like a zero knowledge proof that the response that you got was generated by that model, and the model ran exactly as it was supposed to do. So you can essentially get a zero knowledge proof that the result you got is correct. And finally, we have differential privacy, which was mentioned a little bit before, earlier today. And this is related to the topic of getting a statistical query or answering a statistical query in a way that doesn't reveal information about any individual in a data set. And so, let's say, for example, you have a data set with 3 people and you want to know an average of their height, for example. And some untrusted querier will calculate or will ask for the average height of the group, and it will get an answer. But at this moment, it still doesn't have any information about any particular element. But let's say now we add another element to the group, and then the querier asks for the average again. By having the average for the 3 people and for the 4 people, it's possible to infer the height of the 4th element. So this would break privacy. And so differential privacy is a method to add noise to the answers in a way where the querier will never be able to know the actual height of a new subject. So we'll go a little bit through this in one of the lectures too. So yeah, this is the end of this intro session. So this is the schedule that I'm planning to do. So we have the AI intro today. Tomorrow we'll talk about classification and regression algorithms, so supervised learning. On Wednesday we'll talk about unsupervised learning, so this dimensionality reduction and clustering algorithms, and probably have some practical sessions. So we'll spin up a Google Colab session, which is like a browser interactive session where you can run Python within the browser. And this will allow you to like load the data set and test some of these algorithms in those data sets. On Thursday, I'm going to do a session on neural networks. And on Friday, I'll do a session on privacy for these AI and machine learning algorithms. On the second week, I'll probably only do 3 lectures. So one on reinforcement learning on Monday. On Tuesday, I'll be around, so if you're working on your own projects and you have questions regarding any AI related thing for your own projects, I'll be here and I can go through it with you and give you any kind of tips for your projects. Or if you're interested in just putting anything into practice that you've learned, you can also use this time to come ask me questions or to just explore by yourself. So on Wednesday next week, I'm planning to do a session on natural language processing and generation. And finally on Friday, I'll do a lecture on ChatGPT and AI agents. Finally, week 3 on Tuesday, I'm planning a lecture on computer vision. And finally on Thursday, on image and video generation. So yeah, I think that's it. Yeah, exactly. Do you have any questions from the stuff that I talked about today? Or regarding the plan or anything else? We have 2, maybe 1 there.
Do you know some project or a specific project with CK and anything related to AI? And also if you work with this combination and some examples would be great.
Yeah, so I've never worked in this area or this intersection specifically. I've heard about a few projects that are like doing ZK proofs for machine learning models. I don't know them by heart, but for Friday I'll investigate a few of them and I'll investigate the landscape of what's being built right now and I'll give you like an overview of it.
Thanks.
And the other one?
The methods you talk about privacy in AI, you talk about homomorphic encryption ML.
Mm-hmm.
That works by encrypting every attribute. So every characteristic is encrypted and the model is trained using fully encrypted data.
That's one other option. So the model can be trained on unencrypted data, like normally. But then there's a way to transform this model in a way that it can run on encrypted data, and all of the activations of the neural network are going also to be encrypted, so you get no information about the actual input. The output is also going to be encrypted, so there's no way to decrypt it without a secret key, and then only the client will be able to read it. But the other way is also you can have a model being trained fully on encrypted data. I don't know a lot of examples of these because it's probably just or still a very much in research topic. But once again, on Friday, I'll give you like a clearer picture of this.
And in zero knowledge ML, that involves like the proof is generated fully on the weights of the model. So that if it matches the weights in the model, then it's okay. Then it's right. It's coming from the model, the response.
To be honest, I'm not completely sure how it works. It's something that I'll literally be looking up this week, to be honest, because it's not my area of expertise. I have learned it a little bit a few months ago, but to be honest, I can't answer that question right now.
Thanks.
No? You have a question? Yes.
In the differential privacy, you add noise in the output, right?
Yes.
And is this similar, like, or the FHTML? Because like in FHT we also have noise in every encrypted data.
Yes.
So like differential privacy is kind a FHTML.
No, it's slightly different because you're just adding noise to the answer, but you're not encrypted. For example, if you're looking for the height or the average height of the individuals in a data set, let's say the actual average height is like 180, but then you add a little bit of noise, like a couple centimeters more or less, like
okay.
It's random.
Okay.
And so it's gonna give you like 182. But then if you ask it again, it's gonna give you 178. And then you add another individual, which is like 2 meters tall, and it's going to be, the average is going to be 182 again. So you have no idea what the actual height of the new individual is. Even if it changes the average a little bit, you're not going to know for sure. You might gain a little bit of information based on the change, but it's not enough to, or the goal is to like add enough noise to introduce a certain uncertainty in the like individual records.
No, nice.
All right, any more questions or we can close it off? All right, let's get some coffee then. Thank you all. Okay.